There we go. All right, section 9.1, part 2. So in the beginning of 9.1, we reminded ourselves about arithmetic and geometric sequences. And the reason we look at sequences is because it is a nice beginning step towards series. A sequence is a list of numbers, right, that are set to follow an explicit rule. They're created by following some explicit rule. When we move on to series, instead of having a list of numbers, does anyone know the difference between a series and a sequence? In a series, instead of having the terms separated by commas, a series is a sum of all of the terms. So when we move to series, we take away the commas and we add every term in the sequence. Okay? And that becomes a series. So this is our basic step towards looking at series. What we'll do today is determine if a sequence converges or diverges. And a sequence is said to converge if the limit of the sequence as n goes to infinity approaches a number. Then the sequence converges to that number. Okay? If you take the limit as n goes to infinity of the sequence and it goes to positive infinity or negative infinity, the sequence is said to diverge. So it's simply a limit of the explicit definition of the sequence. All right, so we'll take a look at those. That's what's being said here. And we say that the sequence converges to L if the limit as n goes to infinity of a sub n equals L. Sequences that do not have limits are said to diverge. Before we do any examples with this, in previous years, in the book that we used, early on in the year, we talked about two very special limits. And I don't know if you guys have talked about them, so I want to make sure we have them here. And these limits are two trig limits that make life much, much easier. The limit as x goes to 0 of sine x over x. Does that one look familiar? You have seen it? What is it equal to? 1. It is equal to 1. So, in previous years, we proved this limit graphically, and we looked at a pretty involved proof of this limit. For our purposes, since you guys have already talked about it, we are going to say when you see this limit, you can just say that the limit approaches 1. You don't have to reprove it every time. Okay? So it's a special limit. It helps us if you get this to show up in your problem involving limits of trig, then it makes your life much easier. Okay? Yes, Laura.
So the high limit is converting to it doesn't have a limit.
Correct. Yep. The second special limit that shows up and can be very useful is that one. Have you seen that one? 1 minus cosine x over x. Less familiar. It doesn't come up as often as sine x over x. This one is equal to 0. Yes, is equal to 0. And they're just two limits you want to have in your back pocket. They can make simplifying certain problems much easier. Okay. You will run into this one in the homework for this section. Okay, so now let's try an example. Before we start our example, we need to remember our properties of limits. We've been using limits and derivatives and integrals, which are also versions of limits, all year. So if we are taking the limit of the sum, it is the same as the sum of the limits. We can break it up. We can do that with the difference as well. With limits, different from derivatives and integrals, we can break up a product. The limit of a times b is the same as the limit of a times the limit of b. Okay? Constant multiple, we can always bring a constant that's being multiplied out in front of the limit to make the limit easier to take. Okay? And then quotient rule Again, different from integrals and derivatives, we can simply say the limit of a over b is the limit of a over the limit of b. We can separate it that way. Okay, just a reminder of what we are allowed to do with our limits. So let's look at example 8. Determine whether the sequence converges or diverges. If it converges, find its limits. All right. Well, to find out if a sequence converges or diverges, we just take the limit as n goes to infinity of our sequence. All right, so when we do limits that approach infinity, there are 3 little rules that help us. And you did these rules when you were finding horizontal asymptotes in pre-calc. And they are actually an application of calculus, but let's just think about what these 3 rules are. When you were finding horizontal asymptotes, you were finding a limit without calling it that. And when you had an expression that had something like x to the 5th plus 2x plus 3 over x to the 3rd plus 3x minus 7, something like that, and we were looking for a horizontal asymptote, do you remember what you did? Say it again. You do look at the highest power on both the top and the bottom, because the horizontal asymptote happens when x becomes very, very large. So if x is getting huge, the only powers that are going to make any difference whatsoever are the highest powers. These other powers become negligible. They're so much smaller than something like 1 million cubed versus 1 million. Okay, so really we only have to look at the highest power. And we think about what's happening if we put in a gigantic number to the top and bottom. Well, is the top going to grow faster or the bottom? The top is going to increase without bounds. It's going to go to infinity. And when we had a rational expression like this, we said there was no horizontal asymptote because the top will grow much faster than the bottom and will go to infinity. Well, what we were finding was the limit. And the limit, when the higher power is on top, goes to plus or minus infinity depending on the signs in front of the highest powers. If that were a negative, then it could go to negative infinity. Okay? All right. What if the higher power is on the bottom? What if I have x cubed minus 7x plus 8 over x to the 5th plus 2x minus 20? Goes to 0. Okay. So, again, we're only looking at the highest powers. The bottom is going to grow much faster. It's like having 1 over 1 million, which is really, really tiny and very close to 0. So, in that case, it will go to 0. All right, well, what about when it's the same on the top and bottom? So let's say we have 2x to the 5th plus 3x squared over 3x to the 5th minus 8.
Approaching 2/3.
It's approaching 2/3. So they're growing at the same rate, right? So it's going to approach the ratio of the ratio of the coefficients on the highest powers. So that one will approach 2/3. And we're using the ratio of the coefficients on the highest powers. Okay? So given this little reminder of pre-calc, if I'm taking the limit and then goes to infinity, it's just like finding a horizontal asymptote. What will this one approach? It will approach 2. Does it converge? Yes, then it converges to the number 2. So, if you're asked this, you could say that the sequence converges to 2. All right, easy enough. Questions on that one? All right. Let's move on. Yeah, let's take a look at these two. This is example 9. Determining convergence or divergence. Determine whether the sequence with given nth term converges or diverges. If it converges, find its limit. All right, so let's look at A and B. In both of these, they're presenting the information in a slightly different way. In A, we're getting an explicit definition, and in B, we're getting what kind? Recursive. All right, so let's think about this one. N minus 1 over N, if we want to find out if A sub N converges or diverges, we need to take the limit as N goes to infinity, negative 1 to the N times N minus 1 over N. All right, well, based on the conversation we just had, if we ignore the negative 1 to the N, finding the limit of N minus 1 over N is pretty straightforward. That would approach what? 1. But what is this negative 1 to the N going to do in front of it? When N is even, it'll be positive. And we would end up with positive 1, essentially. And if N is odd, if N is odd, then we get a negative power in front. So, as N gets huge, what's happening is that our sequence is bouncing back and forth between 1 and negative 1. Is it ever converging to one value? No, it's always bouncing back and forth. We call this an oscillating sequence. And that is another situation where the sequence is said to diverge because it does not converge. All right, in part B, they've given us a recursive definition. And when I am given a recursive definition, the first thing I want to do is write out my sequence. Okay, and it's a good practice to always do this with sequences in series. Actually write out what the series looks like, or the sequence in this case. So we have 4 as our first term. What's my next one? Then 10, and so on. So I could come up with an explicit definition for my sequence, but do I need to? Sergey, is that going to converge? No, it's getting huge, right? It's going to continue to get bigger and bigger as it gets bigger. So simply by looking at this, we can see it's not going to converge to any number because it's always getting larger. So this one diverges also. We'll say it increases without bound. And it diverges. And I'll make a note that you could find your A sub N. Your explicit definition, which is going to be 4 plus 2 times N minus 1. And then we could take the limit as N goes to infinity of that. And we would see that it approaches infinity. Okay? Questions on these two? All right. Okay. We good? Okay. So, example 10, you may have seen earlier in the year with limit. It is the sandwich theorem, or the squeeze theorem, you'll see it called sometimes. And it is actually pretty well used when dealing with limits. Not always the easiest theorem to use, but it's nice for you to have seen it. So let's see. Basically what the sandwich theorem says is that if I have a function f of x, and I know that f of x is always between another function g of x and a function h of x, okay? And I know that the limit of g of x and h of x at a point of interest approaches one value, maybe 0 or 1. Well, then I would know that the limit of f of x would also have to approach 1 because it's always in between these two functions. Does that make sense? It's not drawn very nicely here. It doesn't look like they're approaching the same thing. But the idea is f of x is always in between these two. We know that. So if g of x and h of x approach the same value, then f of x at that point would also approach the same value. Would be squeezed in between the two. Okay? So let's see how we can use this. All right, cosine n, show that the sequence cosine n over n converges and find its limit. All right, so cosine n over n, what we need to do is try and think of a function that is always above cosine n over n and another function that is always below cosine n over n. Well, what do we know about cosine? Cosine bounces between what? Cosine n bounces between 1 and negative 1. So that means that cosine n over n would be between 1 over n and negative 1 over n. Right? Because cosine is only going to fall between 1 and negative 1. So we could say cosine n over n will always be less than or equal to 1 over n, and it will always be greater than or equal to negative 1 over n. So given that, we can apply our limit, take the limit as n goes to infinity of every part of this compound inequality. The limit as n goes to infinity of negative 1 over n is less than or equal to the limit as n goes to infinity of cosine n over n is less than or equal to the limit as n goes to infinity of 1 over n. All right, well, what is the limit as n goes to infinity of negative 1 over n? That is 0. What is the limit as n goes to infinity of 1 over n? Also 0. So what does that mean about the limit we're looking for in the middle? Will also go to 0. The one in the middle is the one we're trying to figure out. And we have our solution to our limit. Does cosine n over n converge? Yes. And it converges to 0. All right, questions on that? Not one that you use that often, and you really need to be certain about the fact that our f of x is always between g of x and h of x. So that's the difficulty with it. But it's a pretty useful function when you are certain of the information about your f of x. All right. And then finally, I just want to show you this. We're not going to do any problem with it, but we have something called the absolute value theorem, and it's just a nice, useful tool from time to time. Consider the sequence a sub n If the limit then goes to infinity of the absolute value of a sub n equals 0, then the limit without the absolute value will also go to 0. This only holds when the limit is approaching 0, not some other value. So it's kind of a specific little theorem. And it is proven using the sandwich theorem. We will use this type of theorem when we are looking at convergence of series. So I just wanted you to see it for the first time. We're not going to do any problems with it right now, but it is something that will come back and we will use again. All right. I believe that's it for 9-1. Homework assignment is on the board. So for 9-1, you're doing 31 through 41 odd and 49 through 54. In addition to the 9-2 homework, which is 1 through 25 odd. So we'll move on to 9-2 now. But write down your assignment. I have not gotten the assignment sheet printed yet. So write it down off the board, please.